say we have a buffer solution formed from acetic acid and its conjugate base, sodium acetate. So those molecular formulas are, this is acetic acid. This is the hydrogen that can be donated in the form of a proton for the acid reaction. So sodium acetate would have this molecular formula, and the sodium plus can dissociate upon dissolution of water to form the acetate ion, and this can react in water to produce the acetate ion plus H3O plus. So we're going to use this from our shorthand notation. I'm going to let all of this equal A and write this as HA. So this H is that H. And A stands for what I've circled here. So this would stand for A minus. That would be A minus. So that's how we're using our shorthand notation again, so we don't have to write these big molecular formulas. So we have acetic acid. So we have a mixture of acetic acid and its conjugate base. And so we start with 0.1 molar of the acid and its conjugate base. First, let's find the pH of the buffer solution. So we use the Henderson Hasselbalch equation. Okay, so we'll look up the Ka for acetic acid, and Ka is equal to 1.8 times 10 to the minus fifth. So the pH is going to be pKa, which is negative log of Ka, plus the log of this ratio. Now this ratio is 0.1 divided by 0.1. We're going to use the initial concentrations, and so the log of 1 is 0. So the pH in this case is just the pKa when the initial concentrations are equal. So the pH is equal to 4.7. So this is the pH of our buffer solution. Now let's take this buffer solution and let's add some strong acid to it and see how the pH might change. So we had 0.1 molar acetic acid, 0.1 molar sodium acetate. That's how we formed our buffer solution. We saw the buffer solution has a pH of 4.7. And so now let's add 0.01 molar hydrochloric acid. This is strong acid, and if we added this to pure water, the pH would go from 7 to 2. There'll be a drastic change in the pH. Let's see how the pH will change when we add this to our buffer solution. We're going to add strong acid. So this strong acid will produce H3O plus in solution. So from our reaction, the conjugate base, sodium acetate, can react with that H3O plus to produce acetic acid plus water. And this equilibrium constant is fairly large because, as we saw before, this equilibrium constant is just 1 over Ka. This is just the Ka reaction written in reverse. And Ka is 1.8 times 10 to the minus fifth. So this is 5.6 times 10 to the fourth. So that's a fairly large equilibrium constant. So this reaction lies heavily on products. So basically all of the H3O plus is consumed in this reaction. So now let's find out what the pH would be. So we use the Henderson Hasselbalch equation again. So we have pKa, negative log of 1.8 times 10 to the minus fifth, plus the log of this ratio now. Now this ratio is a little different from the initial amounts because when I added strong acid, I changed the amounts. So we're going to consider this reaction going all the way. And so if I start with 0.01 molar H3O plus, I'm going to produce an additional 0.01 molar HA. So now instead of 0.1 molar HA, I've got 0.1 plus this additional amount, 0.01. So I've added acid. And then I've reacted 0.01 A minus, so instead of 0.1 initially, I have 0.1 minus how much has reacted, and that's 0.01 from the strong acid. So now the values I put in for A minus and HA are 0.1 minus 0.01, and the initial amount 0.1 plus 0.01. So now those initial amounts have changed a little because I reacted the strong acid that I added to the buffer solution. So now let's look at the pH. So when I do this calculation, this turns out to be 0.09. So negative 0.09. So that's almost negative 0.1. So that's just going to change the pH from 4.7 to 4.6. So we only changed the pH by a tenth. It only went down a tenth of a pH unit, even though I added this strong acid. So in pure water, it would have gone from 7 to 2, a change of 5 pH units. In my buffer solution, it only changed by a tenth of a pH unit. So this is how a buffer solution can mitigate the pH change upon addition of a strong acid. Now let's look at what happens when we add a strong base to this buffer. So we'll add 0.01 molar sodium hydroxide, strong base, to this buffer solution. So sodium hydroxide will produce the OH minus ion upon dissolution. So the reaction that will occur now is the acid will react with a strong base. So acetic acid will react with a strong base to produce A minus plus water. Now this is just the reverse of the conjugate base reaction with water. So this equilibrium constant is just 1 over Kb, the conjugate base for acetic acid. So its value would be 1.8 times 10 to the 9th, so 1.8 billion. So this reaction goes essentially to completion. So we're going to consider this reaction going all the way. So if we start with 0.01 molar OH, then we're going to produce 0.01 molar A minus from this reaction. We're going to consider it going to completion because the equilibrium constant is so large. So now, if we write the Henderson Hasselbalch equation, then we have negative log of Ka, and we have plus the log of this ratio. Now, in this case, we start with 0.1 molar A minus. That's our initial amount, 0.1 molar sodium acetate. And we're forming an additional 0.01 molar from this reaction. So we have to account for that in the Henderson Hasselbalch equation. And we started with 0.1 molar of acetic acid, but we just reacted 0.01 molar of it, so we subtract 0.01 molar. So now our concentrations will be 0.1 plus 0.01 divided by 0.1 minus 0.01. And we can calculate the pH. So this gives me a pH of 4.8. So this term right here is equal to 0.09. So we're just raising the pH up by about 1/10 of a pH unit. So in pure water, this would have gone from 7 to 12 by the addition of 0.01 molar sodium hydroxide. But in our buffer solution, it only went up 1/10 from 4.7 to 4.8. So this is how we can add both strong acid and strong base to a buffer solution and keep the pH relatively constant. Now there are a couple of things that you want to keep in mind. Is we can overwhelm the buffer solution if we add too much strong acid or strong base. If I add, say, 0.1 molar, I've reacted all of my acid, and so I don't have a buffer solution anymore. So if I add too much acid or strong base, then I'll overwhelm my buffer solution. And since I have to have both a mixture of HA and H minus, this ratio has to be between, say, 0.1 and 10. So I could write that algebraically as saying and I'll write it in the form of the Henderson Hasselbalch equation, A minus over HA. So this ratio has to be between 0.1 and 10 in order for us to have a valid buffer solution. Otherwise, we want to have a mixture of the two that's robust enough to mitigate pH changes.